Today I'll teach you trigonometry by building this teaching tool in JavaScript. You'll learn trigonometric functions like the sine, cosine, tangent, and their inverses as well. We study these functions in a right triangle at first, and then using the unit circle. You'll learn about radians and how to convert them to degrees and vice versa. You can just watch me explain things, but I recommend you follow along as well to practice some JavaScript. That way you shoot two birds with one stone. Or two pigs with one bird. Get it? Because Angry Birds uses trigonometry to... No!
Gonna code, debug, and have fun. Coding with Radu. Coding with Radu. Gonna prototype and design. Coding with Radu. Coding with Radu. Let's code now.
Let's begin with basic HTML. And because this is just some experimenting with math, I'm going to jump right in and define the canvas. The browser will automatically fill in things like the HTML tag, head, body, and so on. So let's make this canvas 500 by 500, and let's give it a background color of white. I'm going to define the style, and here I'm gonna make the body have a black background color. So in this way, we're gonna see the canvas on top of it. Now let's save the file, refresh the page, and you can see here the canvas now on top of the black body. But I want to remove these margins and these scroll bars from here. So I'm going to go back here and say margin of 0, overflow to hidden. I'm going to refresh. And now the canvas fills in perfectly this screen I have available here. Let's go down and define the script tag. Let's close it so we don't forget to do it. And here I'm just going to type the JavaScript a line to the left like this so I have more space. And I don't want to use external files for this small project. So let me write here a way to access the canvas context. So ctx is going to be my canvas get context to the. And now I'm going to define here 3 points. Point A is going to be at 0, 0 coordinates. Point B is going to be at 90, 120. And point C is going to have the same x coordinate as B. So I'm going to write here b dot x and a y of 0, the same y coordinate as A actually. Now, let's try to draw one of these points. I'm going to draw B, and I will begin a path. Fill style set to black, so that we see it on top of the white canvas. And I'm going to write here an arc at B's location with a radius of, say, 10. And it's going to be a full circle, so starting at 0 degrees and going to math by times 2 radians. This means a full circle. Let's also fill this, save the file, and refresh the page. And we see our point B right here on the canvas. Remember, the 0, 0 coordinate is here in the top left corner, so this is 90 pixels to the right and 120 pixels downwards. Now, I'm not going to copy this for all the other points. I'm going to extract it as a function. So function, draw point. And this is going to take some parameters like the location where we want to draw this point. And then let's give it also a size. The radius here was 10, so I'm going to set the size to 20, the diameter essentially. And let's give it a color set to black by default. So this function now, I'm going to replace here B with this location. here the radius will be size divided by 2, and the color here is going to be set as a parameter. We're going to have different colors later on. Now I'm going to call this function draw point for B. I don't need to specify the other parameters because they have default values there. And let's call it for A and C as well. So now I'm displaying all these 3 points on the canvas. But which is which? It's hard to tell. So let's implement here a function that also draws some text on the canvas. Draw text. And parameters will be text at the given location. And I'm going to draw this text on top of these points. So let's give it a color of white so we can see it. And inside we are going to begin path. Set the fill style to this color. And I want this text to align perfectly in the middle of the dot. So let's have text align to center and text baseline to middle as well. I will set the font, and this time I want to use a bold font with 13 pixels in size, and it's going to be Courier font. Let's fill the text with the given text coming from the parameter, and then at the location X, location Y, and that's it. I'm going to call this function here after drawing the first point. So draw text A. This is going to be the string that's going to be displayed, and then at the location of A, like this. And I'm just going to copy this after drawing the point and after drawing the point for B and for C, like this. Now, if I'm going to save the file and refresh the page, I can see this text appearing on top of these dots right there. But I would like this 0, 0 coordinate to be somehow in the middle of the canvas so that we could see negative coordinates as well. So I'm going to go back up here and define an offset equal to, on the X, it's going to be the width of the canvas divided by 2, so half the canvas. And on the Y, half the height of the canvas. I'm going to call the translate method of the canvas context, and I'm going to pass it the X offset and the Y offset. Let me save this, refresh the page, and you can see now A in the center screen here. This is the new 0, 0 coordinate. Let's actually draw the coordinate system as well. It will make things look more nicely. So I'm going to begin path, move to minus the offset X, and I'm going to line to the width of the canvas, but subtracting this offset so that I don't draw outside the screen. And 0 on the Y. So this is going to be the horizontal line, and same thing for the vertical line. Using the height and the Y offset instead. Let's stroke. Save the file, refresh the page, and we see now these lines indicating how the coordinate system is. Let's draw these a little less striking. So before the stroke here, I'm going to set a line dash of 4, 2. So this is going to be a dashed line with 4 pixels for the dash and 2 spacing. And a line width, let's set it to 1. And the stroke style will be gray, so less emphasized. I'm going to save this and refresh, and now it looks like this. But I should remember here that this set line dash should be reset afterwards. Otherwise, it's going to affect whatever we are going to be drawing next. So I'm going to set here an empty array like this. Let me package this also in its own function. Let's say function draw coordinate system on a given context with a given offset. And align the code in here like this. And I'm going to call the function here, draw coordinate system on CTX with the offset. And let me move the function somewhere down where the drawing functions are. I save, refresh, and everything still works, but the code is cleaner now. Let's add some interaction next. I'm going to go up here and add the event listener for mouse move. I will say document on mouse move. And now let's write a quick arrow function here with the event as a parameter. I'm going to set the B point at the event X, but because we have this offset happening, I need to subtract here offset.x as well. And same thing for the Y. Now, the other point we're going to modify is C, but only on the x-axis, and we will make it be equal to the x-coordinate of B only. And now let's update everything. And let's implement this update function next. So the update function, it's going to refresh every time we move our mouse. So let's clear the canvas before redrawing everything again, starting at minus x offset minus y offset, and then the rectangle will have a width, the same width as the canvas, and the same height as the canvas, like this. Now, okay, I think this part I want it to be up here where we are defining the global variables. And let me just indent all of these function calls to the right. I'm going to close this, save, refresh, and everything is gone now. But when I'm going to move my mouse in the screen, things start working, and they are interactive now. B is always following the mouse, and C is always following the x-coordinate of the mouse. I actually don't like it that when I refresh, everything is blank. So let me just call this update function once up here, and now it's going to trigger that instantly. Now I want to draw lines between these points to make a triangle. So I'm going to go here after drawing the coordinate system, and I will just say draw a line from A to B. We're going to need to implement this function next. And draw a line from A to C, and draw a line from B to C. So this function, I'm going to implement it somewhere here next to draw point. And it will be also a simple function that gets 2 points as a parameter. So P1, P2. And let's have a default color for this one set to black as well. Now I begin a path, set the stroke style to this given color, and let's make it a little bit thicker so it stands out. I'm going to have it 2 pixels this time. And we move to the first point's location and line to the second point's location and stroke. I save the file, refresh the page, and you can see now the triangle forming there. And it's naturally a right triangle with the right angle at C. We're interested in these side lengths next. So let's calculate them. I'm going to write here C is equal to the distance between A and B. A common naming convention is to use lowercase letters for these and have it be the opposite of the points defining the segment. I'm going to copy this two more times, one for A, the distance between B and C, and one for B, the distance between A and C. Now let's draw this information also. So here, after drawing the line from A to B, I'm going to say draw a text. Let's write here C column and concatenate with the value of C calculated as the distance between A and B. But I'm going to round that, otherwise it's going to have very many decimals. And I'm going to draw this text at the average location between A and B, like this. And let's use a black color because previously we were drawing text as white by default. So if we do it the same, we are not going to see anything. Let me now copy this for these other 2 points. So here I'm going to have B between A and C. And here we're going to have A between B and C. Now these functions, average and distance, we don't have them yet, but they are really easy to do. I'm going to go down here and say function average between P1 and P2 is going to be a new point with x equal to P1x plus P2x divided by 2, so the average of the two x values, and same for y. That's it for the average function. And the distance is going to be the length of the hypotenuse. So we are going to return the math hypot between the difference on x and the difference on y. This is essentially using the Pythagorean Theorem. I have a video on that if you want to learn more. Let me close this, save, and refresh. And now you can see these values here changing as I move the mouse. But I think this is becoming a little bit too cluttered. I actually don't need those big points anymore. We're going to focus just on the lengths next. So let me go up here and remove drawing of the points. And because this draw text is now only drawing black text, I'm going to change this to black. And I'm going to remove here this third parameter, like so. This is cleaner already. And I can see that this works. Like, look at A. It's becoming closer and closer to 0. And it's 0 now. And this printing of these values, exact values there, I just did it to verify it if the code works. But I don't really need it anymore. I'm just going to leave here CBA without these values. And I'm going to remove the column as well. Refresh this. And I'm going to style this a little bit more. So let's make the font size a little bit bigger. I'm going to write here 18 pixels. And I want to distinguish this text better because that black line behind it is somehow making it look bad. So I'm going to also stroke the text, and I will say CTX stroke style set to white, same as the background. And let's have a thick line. So CTX line width set to 7 pixels, and stroke text, same as the fill text before filling it. So I'm going to refresh, and now you can see A, B, C much clearer there, and with a little bit of white spacing between the letters and the lines forming the triangle. I like how this looks. And now we're finally ready to discuss trigonometry. It's all about this angle at the center there. Let me go up here and make it clearer. I'm going to say draw text I'm going to call this angle theta. And let's draw this at the location of A, so in the center. Now I'm going to save this, refresh, and you see theta here. So that's the angle that we are going to use to talk about trigonometry. The first trigonometric function that we are going to talk about is the sine function. So the sine is just a name given to the ratio between A and C. So A and C, if we divide A by C, we get the sine of theta. And let me go down here and actually plot this text also on the canvas somewhere. So I'm going to draw text, the sine equal to A divided by C is equal to, and I will concatenate the value of this sine that we have calculated. And let's put this somewhere at, let's say, half offset to the left and 70% of the offset on the y-axis, so downwards. I'm going to save this, refresh, and now you can see this sine value here changing as I'm moving the mouse. And I really don't like that this is so precise. I'm going to put here 2 fixed and 2 as a parameter. So this is going to keep just 2 decimal places. And let's refresh again. And now it's easier to read that value. So what is that value? A divided by C. Well, when the angle is really, really small like this, A becomes essentially 0. So A divided by C, no matter how large C is, it's going to be 0. It's going to be close to 0. Exactly 0 if A is 0. So that's one thing. But then as the angle increases, getting closer and closer to 90 degrees, then what we have here is A divided by C starts to be closer and closer to 1. It is 1 if this triangle is nothing but a line. So that's really what the sine is. It's this ratio of the length opposite to the angle divided by the hypotenuse. Now, knowing the sine of the angle here, we can actually find the angle itself by using the inverse function of the sine. So let's write here theta is equal to math.asin. It stands for arcsine. So arcsine is the inverse function that, given a ratio like this, like A divided by C, will output the angle itself, this theta angle. So I'm going to draw this theta value as well, and I'm just going to copy this below and replace here theta equal to theta. And this will be somewhere on the right side of the screen, so I just changed this minus into a plus. I'm going to save this, refresh, and there's theta. It's 0 here, where the sine is also 0, and up where the sine is 1, theta is 90. It's not 90 degrees. It's 1.57 radians. It's another unit for measuring angles, essentially. And it's what this asin function outputs by default. Now, 1.57 here is half of 3.14, which is pi. So half pi radians means 90 degrees, and pi radians means 180 degrees. So let's actually format this a little nicer here, and I'm going to write a concatenation, and inside the parentheses, I'm going to put, again, rounding so I don't get a lot of decimals, and the value in degrees. So let's call 2 degree of theta. And this is going to be a function that we need to implement next. But it's easy, as I said previously, we just go here and say that 2 degrees, given a value in radians, we just multiply by 180 and divide by pi. So let me close this, save the file, refresh the page, and now you can see theta there in degrees as well, not just in radians, and going all the way to 90 degrees there at the top when the triangle is essentially aligned. I don't like this formatting that when the degrees have just one digit there, it's changing the size of that text. So let me fix that quickly. I'm going to go here and say to string, and then I will pad at the start, considering 2 digits, and I will use a space to do the padding. So a little bit messy code here, doing a lot of things, but I just want to have a space there before that 1 digit to keep everything aligned. I'm a perfectionist. And now that we have the value for theta, we can actually draw an arc there to illustrate the angle. I'll show you. So I'm going to go here and say begin path. Let's set the black stroke style and the line width of 2 again. And we'll use the arc. It's 0, 0 because that's the center of the screen. And I'm going to use a radius of, say, 20. And this will begin at 0, but then it will not go to pi times 2, which we usually do in drawing circles. We're just going to draw until theta, the theta angle. So let's stroke this, and refresh the page, and now you can see that arc being drawn there. Looks nice, but there is a problem. If we're going to go in these other quadrants, it's being drawn in the same place. What we need to do is somehow figure out that here the start angle of the arc should be actually pi or 180, so it jumps on the other side. And then here that it should actually start to go counterclockwise. So this is a tedious thing that I'm just going to go very quickly through because it's just to visualize things nicely. And it's not really trigonometry that much. It's more like programming logic. So I'm just going to write here instead of 0 and theta, start and depending if it's clockwise or not, this is another argument that the arc method supports. So I'm going to define these before calling this arc, and I will say start is equal to, depending on bx and ax, 0 or math pi, so this is for the offset, then a way to figure out if it's clockwise or not. So again, I'm not going to go into the details here, but feel free to study the code if this interests you. And the end is going to be this way as well. And I couldn't figure out if I could do it in one line. Maybe we can, but I just do it with the secondary if statement here. So let's save this, refresh, and now that theta angle is drawn everywhere really nicely. And we can talk about more trigonometry. So sine is just one function. Let's talk about the cosine as well. So the cosine is also a ratio, is actually b divided by c. So it's the length of the side adjacent to the angle, next to the angle, divided also by the hypotenuse. And let me teach you a third function here as well, the tangent. The tangent is actually equal to the sine divided by the cosine. But if you look here and do the math, you'll see that if you do the sine divided by the cosine, it's going to give you a divided by c divided by b divided by c. So c cancels out. So tangent is either the sine divided by the cosine or a divided by b. It's the same thing. You can play around with these if you want. Let me go down here and copy this sine 2 more times for cosine, which is going to be b divided by c cosine 2 fixed. And let's put it a little bit below. And then the tangent, let's say a divided by b. I'm using this variant. And tangent a little bit lower still. I'm going to save this, refresh, and the cosine is a little bit opposite to the sine. You see here where the sine is essentially 0, if I can actually get it there, the cosine is 1. And the cosine is 0 where the sine is 1. But the tangent is a little bit special. It's a divided by b. So even though it's 0 here, same as the sine, it increases. And at this point, a is actually larger than b. So that means that this a divided by b ratio is going to be above 1. When the sine and cosine just go until 1 maximum, this tangent can go above. And actually, here, where b becomes really, really small and a is relatively big, then the tangent approaches infinity. So this is interesting. But I think we can clarify this interface a bit more. I'm going to use colors for a and b, because those are responsible for the sine and cosine, really. And then tangent maybe is a mixture of the two. So I'm going to go here where we have the sine text drawing, and I'm just going to pass red color for the sine. The cosine will be blue, and the tangent will be magenta. This is the combination of red and blue, pretty much. So I'm going to apply the same color coding everywhere for consistency. I'm going to go here when drawing the B. So I'm going to pass blue because B is part of the cosine, which is blue. And I'm going to pass it here also, so the line is blue as well. And the sine, red. The text, a red as well. I'm going to save this. Small error here. Refresh. And now we have some kind of coloring for these things. So you see A is part of the sine, it's red. B is part of the cosine, it's blue. And the tangent is not really visualized on the canvas. It's just the text there, but it's a combination of A and B. So red and blue combined give you magenta. I think that customizing interfaces like this makes it much clearer, at least for me. One thing I want to mention is that these ratios here stay the same if the angle doesn't change. Look at these numbers while I'm increasing the size of this triangle here, but I try to keep the theta the same. So I don't know how well I'm managing to keep theta the same, but I'm trying not to change it with my mouse. And those numbers essentially don't change at all if I could do it properly. But that's really important. The size of the triangle doesn't matter at all. And another thing I want to mention, when we got the value theta here using the arcsine, there are alternative functions that exist for cosine and tangent as well. So arccosine is one that looks for the cosine here. And it's exactly the same result as previously. So theta works as before. And atan with the tangent as well. But I'm going to leave it with the sine as we had previously. Now, let's do even more and study more this behavior, because we know that sine and cosine is between 0 and 1, and there is some kind of relationship. They're almost opposites. but not exactly. I want to plot these values depending on theta. So we're going to use a different canvas for that. And I'm going to go up here and let's add some line breaks. And a new canvas, I'm just going to copy this one. We're going to plot a chart or a graph, depending how you want to call them. I'll use chart because graph in computer science means something else. So the chart is going to be 500 times 100. I won't have so much space at the bottom of this one. And I need to be able to refer to the context of this chart as well. So chart CTX, chart canvas, get context 2D. And let's have an offset for this one as well. So this is going to be chart offset, and it's coming from my canvas width and my canvas height divided by 2. We'll also translate this second context depending on the chart offset. So chart CTX translate depending on those values. And let's draw a coordinate system only once here at the top for the chart context and given the chart offset. You'll see why I don't animate this one as well. Now let's refresh, and it's down here below my console. It's another canvas that is empty for now, but it also has a coordinate system there ready for us to plot points on. So we have a function for drawing points. Actually, it's not even in use now, but it's using the old context. So let's make it use this new one, chart CTX instead. And let's call this draw point in the update function somewhere here at the end. So I'm going to say draw point. The x is going to be the value of theta. The y is going to be the sine value. Let's start with that. And here we have to give it a red color. And now I'm going to save this, refresh the page, and you can see a red dot there. And it's fine. I mean, look at theta, the value here in radians. It's just 0, 1, something like that. The sine here is also between 0 and 1. So what do you expect? It's going to be a point at 0, 0 or close to it, like 1, 1 maximum. It's going to look pretty much the same. So we need to scale these values to be able to see them on this new canvas. And I'm going to define here chart scalar is equal to, let's take the y offset and multiply it like this. Now I refresh, and you can see what happens as the angle changes. Well, now it's drawing the complete line. Let me refresh. So as I am changing this angle, new points are drawn on top of each other. So I'm not clearing that canvas at the bottom. I just let the points accumulate. And that's why I drew that coordinate system only once. I don't want that to be redrawn on every frame. It will look somehow bulky because of anti-aliasing. So this is the sine. Let's repeat this for the cosine as well. So cosine with blue. And let's repeat for the tangent as well. Tangent, magenta. Okay. So you see the sine and cosine are a little bit curved there. And the tangent goes off screen. I think we could see it a little bit better if we make here the scalar maybe something like 0.5. So now the topmost point here and the bottommost point there are -2 and 2. And you can see this shape is a little bit different now. It looks like zoomed out a little bit, and the tangent just goes down. Let's see. I'm going to refresh now, and you can see that tangent going bigger and bigger, and eventually it actually goes down to positive infinity when my mouse x-coordinate is 0. Now, this chart here is quite long on the sides, and that's on purpose, because we're going to extend the definition of the sine, cosine, and tangent to work with angles that are above 90 degrees, and even below 0 degrees. You'll see. We're going to start defining everything in terms of this theta angle. Then we can do angles that are impossible to be part of the triangle itself, because the maximum other angle will be 90 degrees if one is a right angle already. I'm going to go up here and define theta globally using let, because I want to change it somehow. And let's start it with maybe math pi divided by 4. So this is going to be 45 degrees. And I'm going to consider the value of c of this hypotenuse in this triangle fixed. I'm going to set it to, say, 100 pixels. And based on this c and theta, I'm going to define the x and y coordinates of B. This here is the length of that blue segment. And this here is the length of that red segment. So these are actually the sine multiplied by c and the cosine multiplied by c. So I'm going to go here and say math cosine of theta multiplied by c. C just simplifies, and we're left with the length of the blue segment. And same thing happens for the y. Math sine of theta multiplied by c. Now, down here, we really don't need a, b, c anymore. And theta is already given as a global variable. So we are going to change these and calculate the sine based on theta. We will say math sine of theta. The math library has this function for us. And this is going to be math cosine theta. And this is going to be math tangent of theta. Let's save this and refresh. And you can see now that angle there, theta, is exactly 45 degrees. C is equal to 100. This is what we specified it to be here at the top. And then B and A are calculated using the sine and cosine here, the x, y values of point B, essentially. Now I'm going to modify that theta angle using the mouse scroll wheel. You'll see. I go here where we had the previous mouse move event, and I will write on wheel. And let's actually comment these things out for now and just console log this event. It's not a common one, so I want to show you what it looks like in the console. Let me refresh this, and in the console, as I am scrolling upwards, you see something there, and scrolling downwards, you see something else. So downwards, I'm getting this delta y here, 125, and upwards, I get minus 125. So that's the thing we're going to look for, and we're actually going to take the math sine of this event delta y. Now, when I refresh this, I'm going to go upwards. I would like this to be a plus, actually. Somehow going up, I want it to increase. and downwards -1. So a minus in front of this is going to flip it for me. And this is going to be how we modify theta. So theta is going to be minus equals to this value here. And then based on theta, we are going to calculate the b, x, and y as before here. So I just copied this for reference, and the x is going to be this, and the y is going to be this. So let me remove these and the comments, and now save this, refresh the page, and when I'm going to scroll upwards, a big jump happened. Let's see, I'm going to move down this console because these numbers are being hidden right now. So moving downwards, it changes theta here by 1, but in radians. So if I scroll up, it's 1.79, 2.79, 3.79, 5.79. And actually, I can scroll on forever. You can see this number of degrees really goes crazy there. So don't think of theta as the angle itself, but somehow the distance traveled along a circle. We're going to draw a unit circle next. And this is really easy. We just go down here where we have that kind of code I didn't bother to explain previously. And I'm going to remove everything and put here 0 theta. And the radius, let's have it c actually, so that the circle is on the outside. And I refresh, and now we get this as I'm scrolling up. But I don't like that this angle increases so much every time I scroll up. So I'm going to modify this function here so that we modify the value in degrees by 1. So I need to create a similar function to convert to radians here. And I will write 2 radians of this value. And this function is going to be really easy. It's just our 2-degree function, but opposite. So given a degree, we are going to multiply it by math.pi and divide it by 180. And now when I refresh this and I scroll up, you can see the degrees increasing by 1, because every time I scroll up, I actually increase the radians by a very small amount now. And look what happens. We get now negative value for the cosine here. But that's because this blue section, this blue segment, is now on the negative side of the axis. And same will happen eventually when I go with a negative here. Now the sign turns into negative as well. And if I'm going to lower this right here, you can see that this chart continues until we reach this 360-degree moment, but also after that, it continues to infinity. And the tangent, it actually goes minus infinity plus infinity, minus infinity plus infinity, repeatedly like that. And now if I go backwards, this is going to take a while, maybe I just refresh and go backwards. I want to draw this circle differently here. I want it to be counterclockwise if theta is negative. So just give me a sec. I put here theta less than 0. Refresh, and now I go backwards. Now it's better. So now that arc is drawn properly. And if you look here at the chart, you can see these values going towards negative infinity now. So this is periodic function, both sine and cosine just do this wavy thing forever. And the tangent does this positive infinity to negative infinity all the time. Now, this c value here is 100, but I want you to imagine it's 1. I can't make it 1 because then we couldn't see anything. But because these triangles would be anyway similar, then it doesn't matter. The ratios are the same. The sine and cosine are the same. So imagine that that c is 1. I'm going to display it as 1 here. Like when we write c, I'm going to put 1 there. So now you see this is a 1. And actually here, a divided by 1, b divided by 1, essentially that means just a and b. So I'm just going to replace a and b as written here to cosine and sine. In case of a unit circle, the circle that has the radius of 1, that's what the unit circle is, this is just a sine and a cosine. And the only thing we're not visualizing here is the tangent. So we could do that actually. If we would create the right angle triangle here, the length of this side, not the hypotenuse here, but this side right here, that will be the tangent. We could find the coordinates of this point if we apply the Pythagorean theorem here to get this hypotenuse, the x value, y is 0, knowing the tangent and 1 here. So I'm going to go somewhere up here and write, let's name this point T, where it intersects the x-axis. And x is going to be the hypotenuse of 1 and this tangent. And I'm going to multiply it by c because we're scaling everything by this c now. And y of 0. And now when we are drawing these, I'm going to draw a line from B to T. And this is going to be a magenta line. And let's put text there as well. So the tangent at the average location of B and T with the magenta color as well. So I'm going to save this and refresh. And there you have the tangent. So now it's kind of twice this radius here. And you can see it has a value of 2. And as I increase this, notice how the tangent line starts to be parallel to x. And that's why here, where we get this infinity, this crazy thing happening, it never touches x. And that's why it's infinity. Notice also how the tangent function from here doesn't give infinity as the result, as when we did the ratio previously, but it gives us this really large value. And then, I would like to draw this tangent on the other side as well. So let me fix this. I'm going to multiply here with the sine of the cosine. So when we are now on the other side and the cosine is negative, this point of intersection gets flipped on the other side. Okay, I'll just remove this a divided by b since they are not there anymore. I coded this quite fast to focus on explaining the math, so many things can be still improved. Want to give it a try and improve the code? I'll share my version on GitHub and later choose my favorite updates and present them in a video of some kind. See you guys.